All right, hello again. We are the presenters tonight, so there's no need for introductions, I guess, but I'm Kevin Vanden Wymelenberg. Brad Acker is a researcher here at the lab. I believe you know Brad. We're going to talk about commissioning and some case studies, some successes and some not so successful stories about commissioning. But before we get started, as always, I want to make sure we thank the folks who fund the lab series as a total. Better Bricks, Idaho Power, and Northwestern Energy. On behalf of the University of Idaho and Montana State, welcome to the lab series. So I thought I'd talk about our slightly updated mission statement before we got in. And the thing I want to highlight is about 6 months ago, about 8 months ago, we wrote in the keeping pace with the milestones of the 2030 challenge as part of our mission statement, which is an extremely challenging goal. But I wanted to make sure that you all knew we were working on that, and so we should work on that together. The folks who fund us. Okay, setting the stage for commissioning. Familiar with the New Buildings Institute study on LEED energy use? They did about I don't even know exactly the number. Let's just say it was 100. They looked at about 100 LEED buildings and their energy models compared to actual model or actual performance data. And you can get the study on NBI, I think it's .org, but just type in New Buildings Institute, and you'll find this report. And the report, this is one of the charts that just goes through and shows all the different types of projects. The green are the certified, the gray are the silver buildings, the yellow is the gold, and the blue is the platinum buildings. There aren't very many platinum buildings in their survey here. But it shows significant energy savings on the whole, better than CBEX, but a few that actually perform worse than CBEX. I'll go into that in a little more detail here. So here is the line of predicted savings right there. And those that achieved higher than predicted savings, those that achieved lower than predicted savings, and those that achieved lower than predicted and were worse than a code baseline CBEX building. Code baseline building. So why is that? Well, they offer lots of explanations in the paper, and you can read those. But I just wanted to highlight commissioning. You would think commissioning's got a piece. Maybe the ones that were commissioned saved more, and the ones that weren't commissioned didn't save as much. Well, not so. Here is the mean of the set of buildings in their study that didn't receive the advanced commissioning point, and here is the mean of the set of buildings in their study that did receive the advanced commissioning point. So it actually is a little bit lower performance for the folks who did advanced commissioning than the ones who didn't, which is a bit surprising. Generally, it's basically meaningless. It's the same. It's not significantly different. And then also on the folks that had done the measurement and verification over here, again, the means aren't significantly different. In this case, slightly better performance than ones that didn't have the measurement and verification credit. So that starts to put a little hole in this story of we need to make sure we're commissioning all our buildings. Now I'm going to say right away, it's not a very big hole. Commissioning is still absolutely critical. I think what it really does is just say how hard it is to do it well and to actually get the savings that were modeled. It also suggests that there might be some other reasons why the buildings aren't saving the energy that they were predicted to. And I'm going to go through an example of photo controls and daylight savings only, a series of what I call my 7 deadly sins of getting daylight photo controls to perform as they're intended. And that will start to round out some of the other issues behind, I think, the findings of this NBI report.
Do you want questions?
Sure. Jim, go ahead.
If you back up and look at the ones that didn't meet the baseline for the code, even with LEED, you have to comply with the code requirements. How is it that these buildings didn't meet code requirements?
Well, according to the energy models they did, and according to the built and measured data, they did not.
Okay, so they weren't using prescriptive standards, they were going with a model and used the model to satisfy the code requirement.
Right. So they went, yeah. I should say, I'm not sure I actually know the answer to the specific question, but in general, what this graph is showing, all those green dots are measured performance a year after the building was operating.
Oh, okay. So a year later,
other
later. Things could have happened.
Yeah, yeah, like, and a lot of those things we'll kind of hit on here in a minute. Now, the 7 deadly sins for daylight photo controls that I'm going to show are not buildings that were part of this NBI study. This is a separate set of examples. But before I jump into that, I wanted to talk about, and Abhijit Pandey came in a year or two ago and talked on these 2 studies. But just to recap really quickly, the Hesham Mahon group did 2 studies looking at daylighting and photo controls. One was a top lighting or sky lighting study in big box warehouse spaces, and one was a side lighting study in a space like this. And the findings, what they were looking for is something called a realized savings ratio. How much energy was saved compared to what was predicted. So again, measured performance on site after the building was built relative to the energy models. And they looked at 32 spaces and found that a 98% average realized savings ratio with a spread from as little as 25% of the predicted savings being realized to as much as 150%, 156%. But in general, a pretty good average. Top lighting and photo control seems to be working pretty well. Now the study also was followed up a year later, looked at 123 side lit spaces and found a much different story. It said 50% of the spaces that they went to had non-functioning daylight photo controls, period, saving no energy. And the other half that were saving some energy were saving 50% of the predicted, for something like a 25 or 30% average realized savings ratio over the whole sample. And they went through and listed a bunch of reasons why. 17 cases, the sensor set point was too high on the photocell. 7 cases, people had come in and taped over the photocell afterwards. 4 cases, the wires were disconnected. 7 cases, the entire system was inactivated. 5 cases, the wires were never connected after install. 4 cases, the daylight was simply not, there was just not enough daylight to really save any energy. They had the photo control system in a space that wasn't fundamentally daylit. And then finally, one case where the parts weren't compatible with the energy management system. So that that puts some questions, I guess, on that particular issue, and I can talk about that in a different light about the whole daylight photo control issue, but I don't want to spend too much time on that. Instead, I want to focus on some of the other reasons besides, commissioning, why things maybe didn't work as well as they might have. We saw some of the reasons were because they tried to do this energy-saving technology in a space that wasn't basically designed to receive that technology. So they tried to do daylight photo controls in a space that wasn't daylit. You're not going to save any energy. The energy model should show that, but energy models are pretty poor at daylight, actually, at rendering daylight. If you did a separate daylight model, then took those inputs into an energy model, you'd be in better position. Daylight photo controls were never specified in the bid set. Beautifully daylit space, could have saved a lot of energy, but we just went oops on the electrical drawings and didn't get the photo control box and get the circuits relayed such that you could save the energy. So another reason that's not commissioning related. A third one, so we've got it designed well, we've got them specified, but they got value engineered out. Now an energy model could have been built before the value engineering process perhaps got LEED USGBC certification, and then some things didn't quite get into the building. Anyone ever have something they drew into a contract documents not quite make it in the building the way it was supposed to? So, and then here, finally, the commissioning reason, my fourth deadly sin, if it ever pops up. The daylighting was designed, the photo controls were specified, they were installed, and finally they weren't commissioned. They weren't connected and commissioned properly upon install. So there's our 1 out of 7 reasons that are very connected to this commissioning issue. So it starts to paint the picture of why maybe the commissioning point in the NBI study didn't show a greater significance. And then here, users start to come into the fray, right? In this case, it was a switching system, so the lights would switch to half or to off or on full. A pretty nice daylit space, but the people didn't like the switching. They noticed it, and it was one of the 17 that turned the system off or whatever in the Heschong-Mahon group study. Again, these particular projects weren't part of either of the two studies I showed you. What about blinds? Well, people control the blinds, and obviously blinds have something to do with the way lighting energy gets saved or not in a space with photo controls. Now we can imagine similar stories in HVAC systems and other types of building systems as well. And then finally, again, another user input. Comfort, call it aesthetics, call it what you will. But in this particular case, the emergency circuits didn't switch or dim with the rest of the ambient lighting. An alternative might have been to use these guys on the wall sconces as emergency circuits. And this is, you might think that's obvious, but it's they'll start to get to small levels of detail, and you notice it both in the dimmed application here, where that one's more intense, and you notice it definitely when they're actually switched off. So I think those stories start to round out this bigger picture. We're going to talk a lot about commissioning, but we're also going to talk about a lot of other stuff. So mostly we're going to talk about two projects that we had a really deep level of involvement on. One is Cisco. Brad's going to lead you through that. And one is in Cisco Foods warehouse. Brad will tell you where it is. And the other is the Nampa School District story, and specifically the work that we've been doing on Endeavor. And I've talked parts and pieces of that before, but you'll see lots of new stuff today. So with that, Brad's going to take it away for a while.
Uh-oh.
Maybe.
Well, he's getting that around.
Excellent.
The ones that didn't see the savings and the lighting stayed on all the time. As we know with integrated design, you do some trade-offs. Mm-hmm. If they counted on the lighting being dimmed down, that would mean the cooling load would be less because it would be less in space. Mm-hmm. Did they voice any discomfort levels, or did you see cooling systems going beyond their max?
The question is essentially, in spaces that weren't saving the electric lighting energy and the lights were on, did they complain of thermal comfort because the cooling system couldn't keep up with the extra lighting load? And I don't know is the answer specifically, but I haven't heard that much. And on the counterpoint to that, I don't know if I think I've told this story to some of you in the room, but I went and talked with Salt Lake City ASHRAE engineers and basically got from that group a real candid response. And I said, hey, are you willing to size your mechanical systems down a little bit because of photo controls? And they say really no. And they have some reason to say that because of what we've seen in the Heschong-Mahon group study. Now, just because you asked that question, I have to could have talked about two minutes on something I wouldn't have otherwise. But I think there's a couple of interesting pieces to that Heschong-Mahon group study, and that is a space that's better daylit, the photo controls perform better. Now, that sounds like, well, yeah, duh, if you have more daylight, you save more energy. But no, I mean, if it's a better daylit space, people are less likely to override the system because there's a little bit more fudge factor. If you have ample daylight, they're not going to maybe be as concerned about the electric lighting system. Also, these photo control systems function better when there's more light to work with because the dead bands or the set points, you're not trying to cut things so thinly. And so there's a longer talk behind other reasons why we shouldn't give up on daylighting and photo controls, but there is some reason to make sure we're careful when we do design them.
Thanks.
All right, take it over, Brad.
Thank you, Kevin. My name is Brad Acker. I'm one of the researchers here at the lab. So I'm going to be talking about a project we were involved with here at Cisco Foods here in Boise. It's a warehouse facility. And we have some numbers up here.
It's all right. It's a little bit finicky.
No, where can I not go?
Just hit the green.
Okay, all right.
I'll do.
So these numbers here, we have some pretty big nationwide savings, some energy savings from some lighting retrofits that Cisco has been involved in nationwide. And when we see numbers like this, I would hope you would kind of perk up a little bit and say, $2.8 million, that's a lot of money. There's a lot of kilowatt hours here that have been saved, and realize there's a lot of factors that go into numbers like this, and I think we're going to go into some of the many factors which you could run into on a study like this. So our project, our study area was just a small area of the Cisco warehouse out here on Federal Way, and what they did is they installed tubular daylight devices, and they installed completely new lighting system. So they upgraded to T8 fluorescent lights from the high pressure sodium or metal halide lights. We're not exactly sure what they had in there because we came in a little bit after the fact in this study. Originally we were involved in this because Idaho Power approached us and wanted to predict the energy savings with regard to these tubular daylight devices. And we unfortunately just had to tell them that these type of devices are so new and the prediction methods are so unknown that we really can't really predict it reliably right now. So it's just a much, we could really study it after the fact, but couldn't really give reliable numbers ahead of time.
The modeling systems simply can't deal with the tubular daylight devices. They're too complex. And the geeks who write radiance code say, yeah, we're not going to deal with that.
So I think, let's see if I can move this. So over here we just have a layout of the study area, the little circles. Oh, we do have a will I animate in here? All right, so our tubular daylight devices are flying in here. They had 20 tubular daylight devices in the area, 22 of the new T8 lights. And this, I think, is a classical example of they just came in and they put a tubular daylight device every place there was a metal halide light. They threw in some fluorescent lights, seemingly haphazardly. So this is a case where I think the customers could have worked a little closer together with the lighting designers on the vendor's end to get a little bit better lighting in there. And there was also a little bit of question. The lighting threshold, although no one complained about the light levels, it was pretty close to what we were told was the minimum light level dictated by Cisco for this type of work environment. So this is a view of the tubular daylight devices if anyone hasn't seen these before. This is obviously up on the roof. It's a standing seam metal roof. It was a fairly easy install. Modern Roofing here in Boise installed it. They were pretty smart to tell Cisco that they've never done this before. They wanted to install one first and then give a price for the whole package of the 19 other tubular daylight devices. So they went ahead and did that. And I think that showed a lot of intelligence on a contractor's end to say, we're willing to work with this new equipment or new device, but we need to educate ourselves a little bit about it first. And I think if you see that from a contractor, I think that's a good sign rather than a contractor that just jumps in and thinks they know everything about something before they actually use it. So this is a view of the roof system, and then we have a view of some of the lighting equipment here. This was the new T8 fluorescent light. This is a pretty good system. They call it plug and play, where the ballasts just plug into the light tray and the control systems can plug into that. Down here we have a view of the photo sensor, which controls the lighting system. And over here, right out of the box here is our control system, and this is all wireless. You can see little antennas on here. And so it uses just RF signals to control the lights on and off when needed. And we got a view here of some of our data logging equipment. We came into the study, we logged the outside light levels, the light levels underneath the tubular daylight devices. You can see here a little light sensor underneath the tubular daylight device. This is the top of the device. You can see they're only 27 inches long. They just penetrate underneath the insulation of the building, and they don't go down much further than that. And you can see the control system up here on the lighting. This is the light fixture, and then you can see some of our data loggers up here. So we started logging data here on this system, and we just wanted to verify the manufacturer's data. So here you can see some of our logged energy use, and some of our, this blue line here is the outdoor light level, and this red line is the light level underneath the Tubular Daylight device. And you know, we were educating ourselves a lot along the way on these devices too, and we found this pretty interesting phenomena, which was collaborated as well by the manufacturer, that at certain sun angles, the mirrored surface of the Tubular Daylight device really magnifies the sun level. So you can actually get a peak in light levels coming through there at kind of, you know, right before top dead center and right after top dead center on there. So we started looking at our data that we'd been logging, and we started seeing some troubling tendencies. And you could see here that the system was working, the lights shut off, but then the light levels outside started to increase, but the lights just turned back on and for some reason didn't turn back off again. So we got looking into the system and just decided, you know, we needed to do some more commissioning, which really should have been done, you know, probably on the vendor's end more. But we did some more commissioning of the system and some calibration, and we got it to look a lot better. This is really a lot more what we want to see. You know, the light level outside increases and the lights shut off, and just as you'd think, when the light falls, the lights come back on again. But we did have a couple problems with this still. The workers in this area seem to really respond to this hard switching of light levels. It wasn't a very smooth transition from the natural light to the fluorescent lights, and we were experiencing a lot of overriding of the system where they just go shut the system off. And then more importantly, we expected to see some step switching in here. These were supposed to be a 2-ballast light system. It had 4 lamps in there, and they were supposed to switch from 4 lamps to 2 lamps and then off. So it was really here that we discovered that the manufacturer did not send the right stuff. So right about this point, you know, we were thinking we should be able to sit back and log our energy use and just watch the savings, right? They had these new great lights and everything, and they had this really nifty control system, but they didn't have the right ballast, right? So they had to replace the ballast to put basically 2 ballasts on each light, which was going to add another wire onto the control system, which rendered the existing control system obsolete. They had to go replace the control system. And then on top of that, the photo sensors, which controlled this system, wasn't compatible, so they had to come in and change that as well. So as time was marching along, we had a study that we were trying to do, and this was about almost a year later, and we were approaching the deadline for our study, so we really needed to put things into high gear here. So just a little bit on what could have been done better with regard to commissioning this system. As I said, we basically acted as the commissioning agents here. You know, I think people, when they're working with vendors, they need a clear understanding of who's going to commission the system and when it's going to be done. So I think there could have been a lot of closer work with the vendors on that. And then, as I mentioned already too, on the lighting design end, it was a little iffy as to whether or not the lights were all spread out as well as they could be. And when they received all the parts, you know, I think they did a good job of checking that they got the parts they ordered, but it wasn't necessarily the part numbers they ordered with regard to these switching ballasts and things like that. And yeah, the lack of the 2-level switching should have been caught much easier. As I said, it was probably about a year later that these ballasts finally got switched out into the configuration that they ordered. So now a little bit more about the study we actually did. Originally, our methodology was going to be purely measurement and verification. We were going to verify the energy savings of this new system. But because of our time constraints and all the time it took to get the new system put in here, we had to switch our methodologies to more of a predictive energy savings. So what we did is we went out and we measured on the site the actual daylight penetration factor. And daylight penetration factor is a term used with pretty much specific to tubular daylight devices. And it's similar to daylight factor, except they want to highlight the differences in that tubular daylight devices are dependent on sky clearness index and also the solar altitude, along with many physical properties of the tubular daylight device itself, such as the reflectivity of the tube and the dome and the diffuser transmittance. So we went out on site and during all these different solar altitude angles and measured the daylight penetration factor in the space. And then we were able to plot that just using Excel and get a line of best fit. And then what we did is we took our TMY2 weather data, just our typical meteorological year weather data, and we were able to, from our solar altitudes, apply the different daylight penetration factors in order to predict a working plane light level. And then from that working plane light level, we were able to predict energy savings based on the light switching if, and that's a big if, the system is calibrated correctly.
Let me just take a second.
So here we have some comparisons, and what Idaho Power really wanted us to do here was we'll look at the energy savings, not just about the tubular daylight devices, but compare them to skylights and to see how they compared. So what we did is we had actual hard numbers from the installation of the tubular daylight devices, so that was really nice. But then we had to go out and get some estimates. We worked with a lot of vendors here in the valley to get a lot of estimates on skylight installation costs. And we realized that these numbers were pretty variable, depending on our project size, and a lot of vendors, when we were up front about them, about this being, really just a study, that they're dragging their feet a little bit on getting you numbers. But we felt we got some pretty good numbers, and they seemed to agree with some other projects that we had. So we figured we could install about 7.3 skylights for the same money.
He's an engineer.
Yeah.
About 7.3.
Yeah. So I got my saw out and I cut that last skylight in half. But so what we did is we bracketed, when we did our analysis for the skylights, we bracketed that number. So we analyzed the space with 6 skylights in it and then the space with 8 skylights in it to kind of try to account for that variability in our cost estimates. So over here you can kind of see this is the space laid out in one configuration. And then we'll fly in some more skylights here. And we did our analysis of the skylights. We made our models in Ecotect and did the analysis in Radiant, or DaySim.
DaySim.
Yeah. So that's where we got our numbers for that. So this slide is just showing the tubular daylight devices and the energy savings from the system they had in with the metal halide lights. And you can see there's a huge drop just going to a new high efficiency T8 light. They're getting a great energy savings. But then we can also cut that almost into half again using a properly commissioned top lighting strategy. This example is the tubular daylight devices. So you can see we are saving quite a bit of energy in, first of all, just the high efficiency T8 lights, and then a properly commissioned system will get you down even further. So this slide is showing our analysis after we looked at the skylights. And we have the 8 skylights over here and the 6 skylights over here. And you can see that the skylights, as far as electrical energy savings goes, they are performing a little bit better than the tubular daylight devices. So we are saving a little bit more electrical energy per first dollar installed. And again, that could be a pretty variable number. So there could be some variability here, depending on how hard you can squeeze your contractors for a good price on the install. But we didn't really think that was the end of the story, especially if you look at the fenestration area on the roof. You can see there's quite a bit more area exposed to the environments in the skylight scenario here. This is the 8 skylights and the 6 skylights as compared to the tubular daylight devices. So we're obviously going to probably have a pretty big penalty in heating and cooling our space. And this space, although it is not directly cooled, there are cold storage facilities on either side of it. So the temperature of this space would have a large impact on the energy consumption of the adjacent spaces. And we did want this information to apply, to more widely use type spaces. So I don't think this is really the end of the story. We really need to do the energy analysis here to really definitively say what performs better, a tubular daylight device or a skylight. And then on top of all that, then you still get into the whole lighting quality issues of glare and things like that. So
yeah, if you think about it, if they're providing about the same amount of light and one's doing it over a much smaller area, obviously those have to be more intense light sources. And so I think it has to do with lighting energy, total energy flow, and lighting quality. In a warehouse space like we were looking at Cisco, it seemed to be fine. The TDDs or the tubular devices seem to be reasonable. They're really high up out of your field of view, and you're not going like this very often in those kind of spaces, so it seemed to be okay. But if it were a classroom or a gymnasium, you might start to wonder if that would be the right application for a device like that.
In our next slide here, we have some more kind of summary numbers on what our study found. You can see here as we move down this slide, our energy savings is increasing. You can look at our kilowatt hours per square foot per year, decreasing. The first step is quite dramatic from the original lights down to the T8 lights. Then the steps start to get a little bit smaller as we start the 6 skylights and the 8 skylights. But again, this is just with regard to our electrical lighting energy use. And we started toying around with a concept of effective power density. And I think this is a concept which, as the codes get more stringent and as the daylighting strategies get a little more intense, it's something people would really want to look at. And the effective power density is really looking at your scheduled hours that your lights are on versus your total schedule. So your power densities, as you can see here, as they're built, they never change. An installed light is an installed light. But as the number of hours increase that you're not using your lights, your effective power density is dropping. So I think that's a quantity that people or code makers and people that make incentives at the utilities and stuff would probably want to start to look at. So that was a very interesting finding that came out of this study. And some other lessons that we learned along the way in this. It appears that skylights might save more lighting energy than tubular daylight devices. Again, there was just one diameter of tubular daylight devices. We didn't study an array of diameters, so there's a lot of factors there. We need to look at the total energy flow with regard to heating and cooling if we really want a full view of this whole picture. The utilities incentives, when they start to incent these types of devices, might want to look at that whole energy flow and maybe that concept of the effective power density as well. The tubular daylight devices are pretty non-intuitive. We saw that spike in intensity as the sun angle it was a little bit ahead and a little bit below the top dead center, and then there's a lot of weather factors that come into play.
We actually didn't show the slide, but we also found on a cloudy day the light levels provided through the TDDs were higher than on a sunny day. And it's not just the ratio. The actual brightness of the interior space was higher on a cloudy day than on a sunny day, which is, again, completely non-intuitive. And I think it has to do with the view of the sky dome that the mirrored tubular daylight device had, and the total brightness of the entire sky dome relative to the spot brightness of a single solar source. I don't know the physics. It doesn't seem like it's possible, and we didn't confirm it with multiple studies, but we did check it once and checked it again, and it, so.
Yeah. And we found too these we're calling them complex fenestration systems, specifically the tubular daylight devices. The industry is so young; they haven't all worked together yet to develop some of their own standards on ratings. A lot of the better companies, are testing their devices, with regard to just industrial specifications for water tightness and air tightness and things like that. But to be able to compare one product to the other is still fairly difficult at this point in time. And then again, there's probably a lot of code implications and things with regard to this effective power density. And I'm going to hand her back over to Kevin as we start to talk about Endeavor Elementary.
Great. Any questions on Cisco before we move on to our second case study?
What's the diameter of the solar tube?
This one was a 22-inch diameter.
22
That was fairly standard for an industrial application. I've seen 24-inch as well. I think Solitube has a 24-inch. This was actually 22 and a quarter. But yeah, that's it.
And I know you mentioned that you haven't done more research on this, but did you contact the manufacturer to see if they had an explanation about why it was darker or lighter during cloudy days and sunny days?
That specific question we didn't talk much about with the manufacturer. We worked pretty closely. It was Orion Energy Systems was the company that installed. They sell the tubular daylight devices and the lighting systems. They kind of do it as a package. We talked a lot about when we saw this phenomenon about the magnification of the light. That really had me scratching my head, and they confirmed that. And a lot of these guys are holding a lot of their cards pretty close to their chest because it is such a competitive industry right now, and there's so many companies springing up around.
Yeah.
Yeah.
It's worth more investigation. A skylight, you look right on it, tells you its U value, tells you its visible light transmission, and again it comes to the rating systems for the complex fenestration systems. We don't know how to compare these things yet, because you can't write a visible light transmittance on a TDD that changes depending on the solar angle and changes whether it's cloudy, partly cloudy, sunny. So it really starts to put a challenge to the industries with these more innovative products like the solar tracking skylights and those kind of things. The old school metrics aren't going to cut it. There's a large group inside the IESNA working on that kind of stuff, but things take time. Other questions on Cisco? All right. Endeavor. This is a long story, and I'll try to shrink it up a little bit. We've been working with the Nampa School District and Design West Architects on evolving their elementary school prototypes for 6 years or more. Even before the lab was here in Boise, I was working with them out of the Seattle lab. And I'll pick up the story in 2004, right after we came here. And they were designing Willow Creek Elementary School. And it was going out it was going into the design stages. And most of the state is built with prototype schools, so this story pretty well applies to all school districts and lots of different design teams. But there's some efficiency in building the same thing again, and there's some good parts to it, and there's some bad parts to it. So the design really never goes through schematic design again. It kind of jumps into DD, and you make some tweaks and changes. So we were working with the design team and trying to get a picture on what we might do to make some changes in terms of making the school slightly more high performance. The building performs about 10 or 15% above code as a baseline, so better than code as a baseline, and we're trying to help them push it further. So we started by looking at a few schools that were designed in 2000, 2002 range, and I guess 2000, 2001, built and operating in 2002, and noticed some discrepancy specifically on the gas side. More than a 50% or 200% difference here, from $5,000 operating cost to $11,000 for 3 schools that were really designed exactly the same. They had some slightly different orientations and some things like that, but we were pretty shocked at those numbers, and so were they. And so again, it's just another data point in the argument for commissioning. Supposedly they've gone back and cleaned some of this stuff up. I haven't followed up on that specific issue, but it was just a part of the pathway toward this proposal. And so this is we built some energy models and tried to calibrate it to built data. And when you try to calibrate models to built data, you go with a really fine-tooth comb. Well, we got 3 data points on existing buildings, and we found there was lots of variability. So we're trying to figure out which one are we going to calibrate our model to. So that's the backstory, I think, behind this slide. And so we went through a series of, tick out your typical bag of tricks for high performance thing, heat recovery, ventilation, daylighting in the photo controls, daylighting in the gym, photo controls in the gym, additional occupancy sensors, efficient plug loads. So we were looking at, maybe even certain Energy Star type products as part of the package, automatic controls on vending machines, high efficient HVAC systems, et cetera, and showed through this proposal something in the neighborhood of 33 or 35% potential energy dollars saved. And you can see the gas and the electric, and there were some trade-offs there if you look carefully. One of the biggest ones was getting the heat recovery ventilation in to help on the heating side, which then afforded the daylighting to actually work and the electric lighting savings to actually work. This one bit the dust. Willow Creek picked up a few things. They trued up their orientation. They have a great, simple H-plan layout with north and south facing potential classrooms, but it was getting put down on site more or less dictated by bus routes and other fields and things like that. So they decided, okay, we're going to confirm and make sure that all our classrooms are north or south facing. And then they did some modifications to their fenestration so that the south was slightly different than the north in terms of the fenestration design. And they did an energy management system. So that stuff all got in, but the rest of this all got put in as add alternate. And really high bids came back, and it didn't happen. It was right around Katrina and everything too. So basically this got put on the shelf until the next school came around. And in the meantime, the folks over at ESBL were working on the high performance classrooms, and we had the chance to rub elbows with them a little bit and think about some of the things they were looking at for that project. And they had eliminated the cooling system, nearly eliminated the heating system, virtually eliminated the lighting system, a really aggressive daylighting design, and et cetera, and lots of mass and night flush, and using the bodies as the heat for the classroom and just picking up some of the perimeter loads, et cetera. So we took some of those lessons learned, and when Design West came to us in December of 2005, said, hey, we got another school coming to bid here pretty soon. What do we take some of those ideas and apply them to 2 classrooms? We can't get the whole school to go right now, but maybe we can get 2 classrooms put in there and test some ideas out. So that's where the 2 high performance classroom study kind of came out of. That bid, it was accepted. We continued to kind of refine the bid and pulled together a little more incentive money to help pay for some of the add alternate changes as the building was being erected. And this was the proposal at that time. So you won't be able to read this, but you can kind of get a feel for what's happening here. We're trying to reduce the energy use down to a net zero energy classroom. We decided we needed to get the energy use index, EUI, or kBTUs per square foot per year, down to 19. If we could do that, we could convert to all electric consumption and provide the electricity with the south-facing photovoltaic array on the roof of the classroom. So the EUI of the conventional classroom was around 45, super insulated shell 42, optimized glazing and window geometry 39, integrated daylighting and efficient electric lighting 36, passive solar heating and efficient HVAC 33, heat recovery ventilation 30, evap 27, ground source heat pumps, so we changed in the heating, fundamental heating system 23, solar thermal 19, and you can finally meet 19 with the photovoltaic array. So what was installed wasn't all of this stuff, it was parts and pieces. So it was 2 classrooms down a wing, didn't want it to look different from the outside, too late to change a lot of the thermal insulation properties, etc. So we didn't get some of the super insulation here. We did get the chance to change some of the glazing specs. Did get the chance to do electric lighting changes and add daylighting and skylighting to the backs of the space. Passive solar heating was out, but some efficient HVAC, which we'll go into more detail. Heat recovery ventilation, evaporative cooling, those were both in, and that's more or less where we drew the line. So we're thinking in the neighborhood of 27, 30, 33, so 40% reduction from the baseline building. So maybe as much as 50% better than code, 40 to 50% better than code. That's what we're kind of hoping for on the project. In specific, I'll hit the high points, and Brad can come in and fill in some of the details. Daylighting in the back of the classrooms through a series of skylights to balance the luminosity in the space. Changed from the lay-in troffer electric lighting to the indirect direct electric lighting. 1.1 watts per square foot down to 0.75 watts per square foot, I believe it is, on the high performance classrooms. Eliminated the condenser cooling system in favor of a evaporative cooling system, a direct-indirect evaporative cooling system. Eliminated the standard forced air heat with radiant thin tube along the window wall to pick up the perimeter load, and then supplied heat recovery ventilation and a hot water coil in the supply air to pre-temper the air coming into the space so that the ventilation air wasn't feeling too drafty. So those are the fundamental systems changes. I talked about the skylights, and I talked about that we didn't get some of the envelope considerations, and we'll talk more about some of that as we move on here. This spells it out in more detail. In order to do a lot of those things, we needed to kind of be up front with the design team and the school district on elements that they might need to consider. And so again, you're not going to be able to read this, but I'll shout out a few things. We needed 1-inch additional rigid insulation on the roof, which we didn't get on the ceiling. The south view windows in the south classroom needed to have a specific set of properties, which we did get. The skylights needed to have higher visible light transmission and better thermal properties, specifically almost like a triple pane with a translucent membrane in between, so a glazed skylight product. That got value engineered out to CalWall. And the interior design temp needed to be acceptable at 74 degrees, 55 to 60% RH, which is pretty high on the RH side. And we talked about the number of hours out of the year that you might see that. It's basically 3 or 4 weeks in the fall, 3 or 4 weeks in the spring, and it's a non-summer occupied school. So that's a quick and dirty on some of the expectations. This shows the system and heat recovery ventilator, or energy recovery ventilator, and evap system on the roof here, supplying air to both the north and the south classroom. Because it was a little prototype study where we're just doing 2 classrooms, we were forced to have one system that supplied air to that supplied the cooling to the north and the south. Might have been better if we could supply it to 2 north or 2 south. But because we wanted to study a north and a south facing high performance relative to a north and south facing standard, well, this is what we had to do. There's a hot water heater here that replaces that would normally be a gas-fired furnace. That supplies the hot water to the 2 perimeter radiators and also to the little coil and the supply fresh air. What else is worth mentioning on this slide? That's pretty well the summary. And now Brad's going to talk to you, show you some pictures, and talk about some specifics about the system.
Oh boy. This project, made our little lack of switching ballasts over in Cisco look like, summer vacation. We've had a lot of issues with this, and we really wanted to make it work, and it's going to work pretty well here eventually. But I think we were so excited we had this aggressive proposal, and the school board said they would do it. And we were so excited with that victory that I think we dropped the ball a little bit on the subsequent follow-ups of what was really happening behind the scenes with equipment purchases and substitutions and things like that. I made some notes here about specifying equipment, with designs like this, it needs to be done correctly. The purchasing equipment, you can't drop the ball there. You have to really make sure that the right equipment gets purchased. The installation of the equipment has to be right, and especially when we're cutting performance numbers so close to comfort thresholds that everything really needs to be right on. The operation of the equipment has to be right on. There's often a lot of education that needs to happen with some equipment that might not be so everyday to some of these building operators. But to start with here, this is a view of some of the heating equipment and some of our data logging equipment. As you can see, the forced air furnaces here, this is for a standard classroom, which is next door. We have the hot water tank, which will supply our fin tube radiators here in on the exterior walls of the classrooms. And then we had a gas meter to monitor our gas usage. We're monitoring a lot of data points through the energy management system of this building, which was also another victory that the school board decided to use this. I guess they used it on the school previous as well, but that was another step forward to becoming more efficient, was to use an energy management system. So this is just a view of some of the heating components. I guess one that's not in here is our fin tube coil, which was in the supply air stream. We have 100% fresh air system here, which will supply better air quality to the students. And then we used this tempering coil to temper the outside air to take that heating load away. And then the radiators along the exterior wall took the envelope load away. So our first challenge with the heating system was the control aspects. So it wasn't communicated correctly on how to control this system. So our heating coil was being controlled by the room thermostat. And so that was basically not turning on very often, so our outside air was not being tempered. And so we were getting comfort complaints of all this cold air falling down on the occupants. And then you can see these little pumps here in the back. Those are our hot water pumps. And one of those pumps goes to the heating coil, and that wasn't fit with a VFD at the beginning either to provide a little bit more accurate tracking of the supply air temperature. So our first obstacle with regard to the heating was getting the control system ironed out correctly and getting a VFD installed after the fact. And luckily we got to sit back as the mud was being thrown around as to who was paying for the VFD.
And the first issue was a really simple one. It's basically there's a T-stat in the supply air that just needed to be routed to the fan coil as opposed to the T-stat for the room. So that one was free, but it needed to get caught, needed to get noticed. And the ventilation was turned off for a while because they couldn't figure out why it was so cold. So good thing that they had the EMS so they could track back the problem and recognize that it was basically just the wrong T-stat.
And then oddly enough, they not only installed one VFD, they just came in and put a VFD on every pump. So go figure. All right, so we got a view here of some of the ventilation equipment. We got some kind of big photos. All right, so this is a view of some of the heat recovery, cooling, and ventilation equipment, which is up on the roof. They got this neat mechanical ditch or just mechanical space up here on top of the roof. And you can see the evaporative cooler and ventilator here. This is a view of the intake side. We got a picture of the intake filters here. This was another challenge for the maintenance people to get them up there, replacing filters every 3 to 4 months. They're used to replacing filters maybe once a year, and that seems to be a challenge sometimes too, which I'm sure a lot of you are familiar with.
Year-round school, or is this a 9-month?
No, it's a 9-month school. But so this this filter changing was required a little bit more often than usual. And then this service cabinet right here to the side of the intake is what we're looking at here. This is the exhaust fan, and it's kind of hard to see, but this wheel right behind here This is our energy recovery wheel, and this was another challenge in the project. I guess this would be a good time to talk about what was specified versus what was purchased. So we did our due diligence. We studied a lot of schools over in Oregon.
California and Oregon.
California, yeah. We talked to maintenance people, you know, go figure. Someone would want to know how this stuff is to maintain, you know. We're really trying to do right by the school board here. We had their maintenance people talk to the Napa School District maintenance people. You know, hey, these green heck units are specified, they're working well for us, you know, they're not too bad to maintain, this and that. Well, somewhere along the line, when things were getting purchased, things were substituted for, you know, like equivalents, but what was purchased was a couple separate boxes. You know, an energy recovery wheel separate from the evaporative cooling part, separate from the exhaust and supply fan. So now we had a lot of issues with communications internally between the equipment, communications externally to the energy management system, and just, you know, a lot of overall performance issues started popping up. So you can see this little energy recovery wheel here. We ended up getting a full enthalpy wheel, which was recovering sensible and latent heat. And in our designs,
Explain that for the non-engineers.
we specified just a sensible heat wheel. So what our wheel was transferring moisture as well as dry heat, and the wheel that we specified was to transfer, you know, the dry heat only. So as we transferred that moisture, it's changing our design point for our inlet of our evaporative cooling section. So now we're not able to achieve quite as cool a supply air temperature as we could have per our design numbers. So that was one of the many challenges here up here on the roof with this unit. You can see here, this is the evaporative media section. This is a cell deck material, which is basically cardboard. You know, in general, I've heard it should be a pretty good material. We found it to be not very good.
Flaky.
Yeah, we had a lot of problems with it just falling apart. This is kind of the sump down here on the bottom. So normally there's another big piece of cell deck in front of this, and then this piece of PVC is the water header, and this lays on top of the cell deck and just rains the water down on top of this media, and then the water comes down into the sump, and this is the pump here, and comes back up. So initially we were getting a lot of flaking of this media and a lot of just weird kind of cellulose material of some sort in the water, and so it was really clogging up this pump, it was clogging up this header, and we were having a lot of problems with water flow. So we had a lot of water flow issues early on, not only internal to this unit, but because all these pieces were put together as different parts, the functions like the draining of the sump, every time it cycles it should drain the sump and give it fresh water. That became much more challenging. The plumbing of that exit water and where its control valve was, we had problems with that. And when this school first started, they were not hooked up directly to the sewer yet. So they had a holding tank. And so because of the space constraints of this holding tank, and because the plumbing wasn't quite right on the system, we could run it, but it would have to be run with continually fresh water. So you're wasting a lot of water, and we're just filling up that holding tank. So for the first few weeks of school, we couldn't run the system like we wanted. So we kind of started off in a hole with regard to comfort satisfaction of a lot of the occupants in the rooms. So that's, I think, a lot of the issues which we had with the evaporative cooler. Can you think of?
Well, I think we have another slide where we'll hit on a couple of the other points, and then hopefully we can round it back out and talk about some of the things that changed, that we're working on changing so that it's working better in the future.
All right, I lost my, uh-oh. Lost the arrow. Aren't those cute kids?
And it should be picking it back up.
All right. How do I get, oh, there it is. All righty. Okay, moving on, the energy management system. I'm sure a lot of folks here have probably seen these type systems. I think they're really good to help the operators troubleshoot the systems, help the operators just save them from having to run around and see if things are turned on or turned off. And here on this side, we can see this is the high performance classroom schematic of the system. We have 3 hot water pumps, which are all hooked to that hot water heater. The one pump goes up to that tempering coil in the supply duct. Then one pump for each classroom, and it goes out to the fin tube radiators. What's not really represented in here too well is the indirect side of the evaporative cooler. This here blue coil is representing the direct side of the evaporative cooler. And then as the air comes through, we go through an indirect evaporative cooler, which will drop the temperature of the air, and then through our energy recovery wheel, and which would, lower in the summer, lower the temperature of the outside air. So, so this is our high performance classroom. And then here on the other side, is the standard classroom. It's just your typical, fan coil unit. But again, it does have an economizer, so they are saving some energy there. We haven't done any studies to see if, according to this was taken today, the economizers are functioning properly, but that of course has been an issue with economizers functioning or not. So that's just a couple views of the energy management system. I seem to keep on losing the mouse here on the screen.
It scrolls back and forth if you're...
Why don't you, before I scratch it, you want to advance me? Okay. All right. And we got another view here of some of the data points. We're monitoring quite a few data points in the school system. We wanted to get a really good look at the energy savings. Like Kevin said, these are 2 prototype classrooms, which again, I think does have a lot of bearing on especially evaporative cooling, to where, I don't know how many of you, when you were in school, could remember having air conditioning in your schools. It's possible to get by without it, and evaporative cooling, if you don't have any air conditioning, can be pretty nice. But one of our challenges is, you're walking around in a school which is mechanically cooled, nice low relative humidity, and then you walk into this evaporative cool classroom, and there's perception problems there when the comfort, your perceived comfort is not quite as much as it would be otherwise if you're just walking off the playground. But at any rate, this is just an example. We're monitoring the CO2 levels, the light levels, the gas usage, the electrical usage, things like that. So we have a slide here of some of our performance issues. This is pretty much, again, with regard to the ventilation system and the evaporative cooler. We were really trying to figure out what is going on here. You can see the blue line on the bottom is what our vendors told us we should be able to achieve with this equipment. And we're quite a bit above that. We're a little over 5 degrees above that.
Why don't you explain what each line is there real quickly?
All right, yeah, if you can't read. This is the outside air temperature on the very top, this yellowish line. And this black line is the evap in air. So that's the air temperature after the enthalpy wheel, or the energy recovery wheel. So we're dropping our air temperature a little bit on that energy recovery wheel. And then these other series of lines are various points in the duct system. After the heating coil, we were concerned that we were picking up some heat from this heating coil. Eventually, we'd shut the valves off to that hot water tank. But we were a little concerned about that. We have the evaporative cooler out is this red line. And this, the purple line is the grill of the room. So we were picking up a little bit of duct heat, but it wasn't any more than what should be expected. But again, I talked a lot about some of the issues we had with the clogged pumps and the evaporative cooler, the building not being connected to the sewer, the drain valve problems. One interesting problem is we had a lot of odor. We had some odor concerns, and we're out in Napa, and a lot of you are probably fairly familiar with some of the ag industry out there. And so we had odor complaints related to just smells that were in the environment, but because of our 100% outside air system, were being brought into the room. Luckily, that didn't persist.
Yeah. It was
very,
kind of obscure,
very long.
short complaint.
So yeah, so that kind of took us up to about this spring, the spring of 2008. And then we started, as the system still wasn't performing, we started looking more at some of these issues that we had specified in some of the documents about the insulation levels in the ceiling and the properties of the windows and the properties of the skylights and things like that. And I think a lot of those are just adding up for cumulative effects to degrade our performance a little bit. And eventually, Bill with Musgrove, he had a little bit more of a common sense approach. Eventually, we took our room temperatures, basically our return air temperatures, and said, well, okay, at the manufactured efficiencies of this equipment, can we take this temperature air and deliver the temperature we want? And I think we were figuring out that maybe from some of these issues of insulation levels not being quite right, and maybe getting some stagnant air in some of these high light wells, that we were our exhaust air was perhaps a little too warm to be able to actually cool down to where we wanted to.
And I just wanted to clarify that Musgrove was brought in as an external consultant to help troubleshoot the issue.
Yeah. So we've done things. We've kind of maxed out the face velocity on this evaporative cooler right now. So
that means we can't put any more air through the thing without,
we'll have a lot of carryover if we, we'd like to up our CFM with a fan unit, but if we do, we're just going to be blowing water right through the evaporative media into the duct system, and there's a whole range of problems associated with that. So right now we're looking at maybe adding some above ceiling, those little turbo fans, and putting a couple more diffusers in, and just getting some more airflow in the space because the relative humidity is a little higher than we want it, and if we can just get some more airflow, we get that perceived cooling
Think
effect.
Ceiling fan, but we only have 10 feet, so we don't have room for a real ceiling fan, so we're doing these kind of alternate airflow ideas.
Yeah. And then ultimately the school board, when we presented this to them, this 74 degrees, 55 to 60% relative humidity was thought to be acceptable. And at the end of the day, maybe that's pushing the comfort threshold a little too far. That could be another issue we're looking at here.
Three things, maybe you're going to get to these, but the three things that we're hoping to work through next are get that full enthalpy wheel replaced with is it sensible only?
Yeah.
Sensible only. And then eliminate this morning heating that's happening where it's cool outside, and so they're heating in the morning, and then we're trying to cool in the afternoon. Try to deal with a little bit lower acceptable minimum air temp for mornings where we expect cooling in the afternoon. And the third one is work through some night flush ideas, because we're not taking advantage of the night flush right now. Were there other things that we're working through?
That's about it. Again, like with regard to this, the night flush and the heating in the morning, again, that's kind of a control issue on the control strategy being communicated well to the folks that are in charge of that. And there are some issues, I think, with the training too. When we were taking some of these data points, we had to go out and instrument a lot more than what we have out there right now. So one of the maintenance staff was going to put the system into occupied over the weekend, so I could collect a bunch of data over the weekend. Well, he couldn't even figure out how to put it into occupied on the energy management system. So that was kind of a red flag too, that maybe there needs to be a little more training here with some of this.
It's not his fault.
With some of this equipment. No, of course it's not his fault, but it was a little bit of a.
And there was one other
matter.
thing I think we had in here that we wanted to hit on, and that was when the outside supply air is cooler than the return air, we're actually heating the supply air with our enthalpy wheel. And does that make sense? So we're not doing ourselves a favor by using the enthalpy wheel when our outside air is actually cooler than our return air. But we can't find the control to dictate, okay, turn it on now and don't turn it on now. We're working through trying to figure that out. So.
Again, that was a
Yeah. Right.
Yeah, that was an issue again with having 3 boxes of equipment up there from 3 different manufacturers versus our 1 box, our green heck unit that we specified, had those controls internal, and that was another issue that fell out of that. And again, I said it earlier, we were just so excited on getting this bought off by the school board that we didn't pay a lot of attention in the design phase.
In the supply, I guess the supply of purchasing phase.
Yeah, so we should have been kind of at that table more, screaming, jumping up and down.
Millions of dollars were saved by having separate units.
I actually believe it was more expensive.
Definitely in the long run.
Yeah, even for up front, I believe it was, but I can't verify that.
And this next slide shows a little bit of the good. Well, there's a lot of good in this school. The lighting was excellent. It's just this heating and cooling part has been a real pain. But the indoor air quality is a lot better in the high performance classrooms than the standard classrooms. A lot of times when you look at indoor air quality and especially CO2 levels, people not only look at the average levels, but the peak levels are very important. And you can see this peak level a little bit above 1400, and I don't think we're not monitoring the background CO2 level, which we probably should be, just the outdoor CO2 level. But obviously, it can't be that high because our high performance indoor CO2 levels are fairly low. Both these numbers are really good. Anything above 1,000, starts to be questionable as far as indoor air quality goes. So you can see our maximum levels on our standard classrooms exceed that by quite a bit. So we're doing pretty good on our indoor air quality. So that's good. And I'm going to give it back to Kevin so he can talk some more about the lighting.
Questions on heating, cooling, ventilating, all the series of issues? Ken?
Mr. Baker.
I'll come up closer to the
Thank
mic, but I guess what I'm wondering watching this is, did you choose 2 of the regular classrooms and monitor them for the issues? Were there also issues in the other classrooms? We're just not hearing about those. We're hearing about the issues in the high performance.
Yeah, thank you, Ken. We're logging lots of data, and we've been focusing right now on the trying to put out fires. So we have an immense amount to go through and actually do more of what you're suggesting. So we're not hearing about the complaints. That doesn't mean there aren't some things not working properly. The CO2 that we just showed, that's a pretty significant difference. We want to find out what's going on there. First order of business is try not to get the equipment that's installed and not performing up to standards. Make sure it doesn't get yanked and replaced. So that's how serious I think these issues are right now. The other issue about that, and kind of follow up to your question, is what you do in 2 classrooms versus what you do over the whole school. Now, we already know that they've been installing the standard classroom equipment for a long time now. They make small incremental changes, but by and large, they've got a lot of experience putting this stuff in and getting it to operate. The 2 classrooms are obviously, 1, a lot different, and 2, there's only 2 of them. And so when they went ahead and installed these things, maybe we didn't really need to care about them because there were only 2, and maybe these 2 little oddballs over here that we didn't have time to deal with as carefully as if the whole school would have been designed that way. So there are pluses and minuses to doing this high performance prototype or 2 classroom analysis. The pluses are we don't make these mistakes on the whole school. The minuses are maybe we wouldn't have made some of those mistakes if it was designed for the whole school. So that's a little bit tangential to what you were saying. We have about 15 minutes left, and I want to hit on a couple of things. on the lighting. But before we do that, are there other questions on the heating, ventilating, cooling? Okay, so the lighting is working great. The teachers love it. The energy is being saved. I'll show you some charts. Not having any complaints about the lights being noticeably dimming or switching on and off all the time. It is a full dimming system, 100% down to 10%. At the 10% light output, you're probably putting 21% power into the system to keep the ballast burning and whatnot. But nonetheless, a pretty aggressive system. It'll switch off. At its off, it'll switch back on to dim and ramp back up from there. I believe it's a watt stopper control system and Lightalier, maybe, on the electric lighting fixtures, I can't recall. The standard classrooms are these lay-in troffers, as I mentioned before. I did it. 1.1 watts a square foot, 1 lamp on, 2 lamps on, or all 3 lamps on. Wall switches at the door. On this school, they actually put a wall switch over here at the classroom to hit the classroom light. You know what? That might only be in the high-performance classrooms. I think it is. Here you can see the south window configuration. The north window is different, but this is the standard classroom. These are the 2 high-performance classrooms with the skylights at the back of the space. One of the challenges of the study was to find 4 classrooms in the middle of a wing. So we could do 2 north and south high-performance, 2 north and south standard. But to get 4 in the middle of the wing, it dictated that we use the 4 that are also the tutor classrooms. And so they have these big chunks cut out of them here for the tutoring. These are little private tutor spaces accessed from the hallway. And that did something to the daylight to sort of push it away from the occupied space. And so in future designs, we've worked on pulling that daylight a little bit closer into where the kids sit. You can see it's more like at the back wall here. Nonetheless, there's a large relight window to help improve the perceived brightness across the space. Here's the north classroom window fenestration. You can see the indirect, direct, mostly up, actually mostly down light, direct, indirect fixtures here. This is a 2-lamp cross section with, I believe, 1 ballast per fixture, full dimming ballasts. Photocell is mounted up in the light well here. There's a little toggle on the photocell to dictate whether you're looking at a skylight or out a view window, just in terms of its ability to assess the lighting at different levels, because at a skylight level it's a much higher level typically. So I guess its accuracy range, there's a little toggle. We decided to do that as opposed to point it out the window, because it sees brown when you install it, it sees green when the grass grows, it sees white when it snows. And that obviously has a lot to do with the illumination it picks up, and therefore the lighting might do a little bit more funky stuff. So this is a skylight or open loop system where it doesn't see the electric lighting, and it's a skylight application for a little bit more consistency. It's translucent light up here through the skylight, so again, it's not going to pick up sunspots or things like that. All in all, it's working really well. Question?
Did you measure the light levels in this classroom throughout the year? And what my question is going to is, did it dramatically increase when there's a full snow ground cover?
We haven't looked at it in detail when there's a snow ground cover versus not. But the concern we had is that photocell could be mounted in a skylight well, looking at a skylight, or at about 6 or 8, maybe 10 feet off the window wall, looking out a window wall. But when it does it, it looks at the ground. So that was the concern.
You know, your skylight's looking up, and if you've got a snow ground cover,
right,
you're getting the high reflectivity into the space.
That's true.
Off the ground.
Yeah, and you might be not saving some of the energy you could.
Yeah.
That's true, yeah. Generally, we err on the side of more comfort and a little less energy savings. But yeah, that's true. That's true. We are monitoring. It's hard to monitor illumination at a work plane throughout a year. So because of it gets in the way of people, right? So we have one photocell that runs the control system, and we have that's in the skylight well. We have another one just centered on the middle of the space, logging illumination, looking down, and we can interpolate from that how much illumination might be falling on that surface. Here's a little bit more about the skylight well, just so you can see. some of the architecture behind it. Four, I don't want to get lost here. 4 cow wall. This is the north side classroom. These are tipped up facing south. Probably didn't need to do that, but the idea was it'd punch a little bit more direct sun into the space. Here they are, one inside the tutoring room. One of the issues in the tutoring room, as we learned, was acoustics. A tall space, lots of hard surfaces, so we had to come back in and work with, they pulled a few tectum panels that were left in the trash from the gymnasium and put them up from when they were installing the gymnasium acoustics, and they put them up in these zones here and put some pegboards on the walls. It's a lot better. That was an unforeseen concern. We're also logging occupancy in the 2 tutor rooms that have the skylights versus the 2 that don't, because they have the option to choose any of the 4. So we want to see if people choose the 2 that have skylights more often than not. Haven't had the chance to analyze that yet. This was when we were in there lighting and doing the lighting commissioning. It's unfortunately up on a ladder. Good news is people can't mess with it. Bad news is it's kind of hard to get to. Could have been in a locked closet, the HVAC closet right around the corner or something. Question, like I said, this is working great, so no problems here. But we commissioned it like this, white bare walls everywhere. This is what the classroom looks like now. Brown, relatively dark pegboards in a lot of spaces. And so, yeah, they picked a low VOC pegboard. Unfortunately, it was dark brown is the only color it came in. They needed a lighter color there, but because it does have a lot of implications to the lighting. In this case, there's enough daylight. I guess, again, the fudge factor that it's not a problem. I'll show you the lighting energy saved here.
Was the electrical engineer aware of that? Those colors coming in?
Don't know. I wasn't, and I was pretty involved on the project. So let's see here. Here's the blue bar is the code compliant lighting. The red bar is the standard classroom measured data. The standard class, that is, so again, it's more like this efficacy piece. They basically installed code lighting in the space. So if they were running full on all the time, they would have been using this much energy. Because of occupancy and other issues, they're saving a significant amount of energy in the standard classrooms, even more in the high performance classrooms.
So the lighting controls are occupancy sensors too?
Occupancy sensors are in the standard classrooms as well as the high performance classrooms.
Okay.
Yeah. Here is your designed watts per square foot, 1.1 and 0.8. I guess I thought it was 0.75, but it's 0.8. And as measured, effectively 0.67 for the standard classroom and 0.47 for the measured. So in Heschong-Mahon group study would have been part of the small sample that was saving significantly more than predicted, which is great. And I'm going to end it there for our investigation of this study. I had some slides to show you about blind use, but we'll save those for another day. And unless there's questions about lighting, I want to spend the last 5 minutes on another thing, and for something different. Any questions on lighting? Okay. So, how many of you were at the energy conference? Good chunky. So a lot of you got to see Ed Mazaria in the morning, I hope. Talking about the 2030 challenge. Okay, this needs to be grilled into our brains. AIA, ASHRAE, all have signed on, so our professional organizations say we have to do this stuff. The 2030 challenge is to reduce fossil fuel-based energy in buildings by 60% by the year 2010, and 10% more or less every 5 years thereafter to be carbon neutral by the year 2030. That's the challenge. Right now, the idea is to build anything right now 50% better so that by 2010 we can work up to be 60% better. And they've put out a little table that shows you the code equivalents, and we're at IECC 2006 here, and it's better than what? It's not better than actually a code baseline building. It's better than the annual or the US average Commercial Building Stock Energy Use Survey, CBEX. And so it's a little bit better, a little bit easier to get there. So for IECC 2006, right now we need to be 30% better to be 50% better than the CBEX. 30% better than IECC, to be 50% better than CBEX. And really, buildings and design right now are going to be operating by the year 2010, and our goal should really be about 35 or 40% better than IECC as a minimum and everything we build. So this is really scary and really hard to do. And I was trying to buddy up with Ed when he was here. I'm not sure how successful I was, but I'm trying to, with U of O, we're trying to pitch this idea of making the 2030 regional and putting some resources behind it. The vision and the goal is great, but what about the resources behind it? Now, you all know how we work, and we want to keep doing what we do and work with you that way. But we're also trying to open this up to something that we're calling the Building Carbon Neutral Initiative. This was a small piece of funding that got that U of O and we shared by EPA. And this is the first time I've ever said it to anybody, so you're the first to get the info. If you go to www.buildingcarbonneutral.org, you'll see this webpage here. And it's not formally connected to 2030 yet, though someday I'd like it to be and have a kind of regional resource to help meet the 2030 challenge. What it's got that as its initiative. So you can read up here about the initiative. You can say, just like you can join the 2030 challenge, you could join this initiative. I'm not so concerned about that really. But the online resources and the energy consulting. Right now, energy consulting just sort of connects you to the lab resources, and maybe eventually have some professional partners that could be on there. But the online resources, the project was basically funded to do this online resource called the what we'll simply call the Climate Responsive Design Web Tool. And this is, if you click that Climate Responsive Design Web Tool under online resources, you'll see this chart come up. The idea is to get a lot more of these types of charts, where here's just raw data. You can look at dry bulb or relative humidity for all these climate zones. You can click on these different color schemes to help decipher the information. This is all based on TMY2. If we get more funding, we'd like to open it up to all the TMY3 sites as well in the Northwest. This is where you can look at, based upon that weather, where heating or cooling is needed. So you click this chart, and up comes a heating chart or cooling chart based upon a building balance point temperature, which you have the ability to slide here. Or here, this chart is looking at evaporative cooling potential. I'll show you what that looks like next. And then down here is a whole bunch of other charts, probably 30 or 40 other ways to slice up climate data and tie and connect it to building systems ideas about energy efficiency. So the big premise was to put climate data in a design-based mentality, connected with specific energy efficiency features. We haven't really had anyone pilot it yet, so go check out the site, take a look at it. I'll just show you two screenshots from the site, if they ever come up, and then we'll be done. So here is the chart for evaporative cooling potential. All the blue areas are where cooling is not needed based upon a certain balance point temperature and a certain max dry bulb temperature and max relative humidity here, and you have the ability to scroll these to select whichever is your comfort criteria. The green hours are the hours out of the year, and it's a certain percentage and a certain number of hours where you can meet the load by evap cooling, and here's a certain number of hours out of the year where you couldn't meet the load by evap cooling. There's a series of assumptions laid behind this, and we want to get to the tool so where you can click on and get all the detailed assumptions, but we didn't have the funding to get all the way there. But these two are two of the big assumptions, and so you have the ability to use the scroll bars here and choose different set points acceptable. This one is 78 degrees at 55% relative humidity. It says you can meet all the loads, again, based upon a certain internal load assumption. And that's what we need to get that stuff live for you to see. But and the last slide here is looking at one of the other charts where it's not as interactive. It's just sort of plotting data in a bunch of different ways. This one is looking at stack versus cross ventilation. I'll have to squat down here to read. The black are the hours where cooling is not needed. The green are the hours where cross ventilation is possible due to a certain assumption on wind speed and a certain assumption about depth distance between window walls, and the white hours are where stack ventilation is required because there's not enough wind speed. So that's one of 30 or 35 different types of ways that we've sliced up the data. So take a look at it. I'd love to hear your feedback on it. If you're compelled, you can join the initiative or not, but I just wanted to share that with you all. So that's it. Thank you. Thanks to Idaho Power, University of Idaho, Montana State University, Northwestern Energy, and Better Bricks. They didn't pay us for tonight, but I suppose they pay our salary, so they paid us tonight. And thanks for coming.